Okay, hello everyone. You should be able to hear me, I think. Um, let's see. Yes, this seems to be working. Good. Give me a thumbs up if you can hear me. Okay, thank you. Yes, some dancing is allowed too. Excellent, very well. Um, so today we're gonna continue with angular momentum. We're actually gonna close out that chapter. So last time we introduced angular momentum, and we talked a little bit just at the end of class about conservation of angular momentum. So we're going to take that a little bit further today, compare it with linear momentum and conservation of linear momentum, and then we're going to talk about precession as something that follows from conservation of angular momentum. So just as a reminder, again, angular momentum is the cross product of the vector from the origin, which is where our axis is, to the point where the momentum applies for a single particle, and the cross product of that vector r with the linear momentum vector p. So for a single particle, angular momentum is defined as L is r cross p. For multiple particles, we just add up the individual angular momenta. So if we have 10 particles right in some system interacting with each other or not interacting with each other, whatever the case may be, then the total angular momentum for that system of particles is going to be the sum of their individual angular momenta. And then for a rigid body or an extended object, continuous mass distribution, we determined that the angular momentum is the moment of inertia times the angular velocity. And in this case, this is the moment of inertia around the axis given by the rotational, the angular velocity, the rotational axis at that time. So again, of course, there's a lot of similarities to linear momentum. All of this is very similar. We had a linear momentum for a single particle that was m cross v, although that's not the part that is very similar here. Well, I mean, I guess you could say it's similar to the last expression here, but for an individual particle, it's not really similar. We constructed the total momentum, which was a sum over the individual momentum components in a system of particles. And then we actually constructed from this the expression for Newton's second law, which is that the change in the linear momentum over time is equal to the net external force applied to that system. And that's, of course, something that comes back here in the angular momentum situation as well, except now we have that the change in the angular momentum of either a system of particles, of a rigid body around some axis, rigid body. So this was, let me just make sure this is single particle, and this is a collection or multiple particles. So dl dt, the change in the angular momentum, is given by or caused by the net external torque on that system. So again, very similar expressions here for linear and angular momentum. Now, conservation of angular momentum is also very similar. Angular, what am I writing here? Angular momentum. That's very similar to conservation of linear momentum. That just says that the angular momentum before some interaction is going to be equal to the angular momentum after some interaction. Again, here we had conservation of linear momentum that we've covered before. And that said that the total momentum before, let's say, some collision is equal to the total momentum after some collision. That's of course true if this component is equal to 0. If no net external torque is applied. And in this case it was if there's no net external force. So very similar, very parallel expressions here. And we can look at that in an example. We're going to skip this here. We're going to skip this as just a picture for the extended body, for the rigid body. So we can look at this conservation of angular momentum. A typical example is an ice skater, right? So we have an ice skater who's skating is spinning around in a circle and around her own axis here with an angular velocity omega. And the ice skater has a moment of inertia I. So the angular momentum of the ice skater is I times omega. This is with arms extended. So as you know, and to be honest, I can trust more that you know about ice skating here than I could in the past decade when I was teaching in the southern USA, where ice skating was not as common. So you know that if you extend your arms, then of course you're going to spin less quickly, more slowly than if you pull your arms in and you make yourself small. You get all of your mass close to the rotational axis. So that's a second situation we can write down now. There will be a different angular velocity omega prime, and there will be a different moment of inertia because the mass distribution has changed for this ice skater. So we have a before situation, an after situation. In both cases, we can write down the angular momentum. I guess there should have been a prime here for this to be L prime. And that angular momentum before and after this action of pulling in the extended arms, those angular momenta will have to be equal to each other. Why is that? Because the net external torque is 0. There's no external torque that is applied to the ice skater when she pulls in her arms, right? There may be some internal things that are happening. Clearly, there is a change. Some forces have to be applied by the ice skater to pull her arms in, but there's no external net torque that is applied. There also wouldn't be any location for the torque to apply if we assume that she's standing on the tip of her skate, and there's no place where a force would be able to apply except at the tip of the skate, and then we know that we're actually in the axis of rotation, so the torque would be 0 for any force that applies there as well, anyway. So we have for the ice skater, for our example with the ice skater, that the angular momentum before, which was I times omega, will have to be equal to the angular momentum after, or L prime, which is I prime times omega prime. We can use this to calculate now what, and before I calculate what omega prime is, let's say what is the connection between I and I prime. So this is with arms extended, and this is with arms pulled in. So which one is larger? Is I larger than I prime, or is I prime larger than I, or are they the same? So put the answers that you think it is in the chat. So remember that the moment of inertia is determined primarily by objects that are far away from the axis of rotation. So when the arms are extended, there's more mass far away from the axis of rotation, so I will be larger, right? The mass is away from the axis of rotation. So if I is greater than I prime, now we can go back to our expression here. We can solve this expression for omega prime. Omega prime will be I over I prime times the original omega. And if I is greater than, let's see, if I is greater than I prime, then that means that omega prime will be greater than omega, right? So when you pull your arms in, then that means you're going to have a faster rotation, a faster angular velocity with your arms pulled in. And so let's look at that again on the picture now. So what happens is that if L is I times omega has to remain constant, and I decreases, then omega will of course have to increase to make up for the decrease in for the decrease in I. So let's look now at the kinetic energy. So what about the kinetic energy? So we have a kinetic energy before, which is 1/2 I times omega squared. That's our expression for kinetic energy in rotational and angular motion problems. Afterwards, we have a kinetic energy that's 1/2 times I prime omega prime squared. So how do we relate those kinetic energies now? Well, let's look at the kinetic energy after. We can write this as 1/2 I prime omega prime. I mean, there's different ways to do this, but I'm going to do it this way. I'll split off that one factor I prime omega prime, and then I have one remaining factor of omega prime. So now I can write this as 1/2 I omega, because this is just our expression for our L prime, or our expression for L for that matter. And then we have one more remaining omega prime. But we know that omega prime is I over I prime times omega. So that means that this is going to be 1/2 I omega, and then I have I over I prime times omega, or I over I prime times K B4. So again, I was greater than I prime, so K B4 will be, well, so will this be greater or smaller than the kinetic energy after? So which one's greater, the kinetic energy before or the kinetic energy after? So the kinetic energy after pulling in your arms is going to be greater. So again, there's a similarity here with the problems in linear momentum, which is that in linear momentum, note we had a couple of things that we said were always true, and then there were some things that were sometimes true, right? The thing that was always true in linear momentum, translational motion problems, was that momentum was always conserved, but kinetic energy was only constant in some cases, namely in cases of elastic collisions. So the same thing is true in rotational motion with angular momentum. Angular momentum is always conserved. Angular momentum is always conserved, as long as there's no net external torque. But kinetic energy is not always constant. Kinetic energy is only constant. Kinetic energy is only constant when the work done is equal to 0. Because we know then we can write our work energy theorem, delta K is equal to minus W with the work done by external forces So if the work is equal to 0, then kinetic energy is constant. Otherwise, it's not. And so here, of course, it is not the case that the work is equal to 0. Because now this doesn't just include, this includes now all kinds of work. And then in particular, the ice skater here has to do work to pull in her arms. As you know, also from possibly personal experience, when you're ice skating or when you're spinning around, if you want to pull in your arms, you actually have to do work to pull them in. And what you're actually doing then is you are doing work to increase your own rotational kinetic energy, in this case, in the case of ice skating, right? So in that case, the work that is done goes into increasing your kinetic energy. And so you could think of this as a non-elastic situation. Of course, there's no collision. It's just comparing two different situations before and after. There's not really an equivalent to this in the linear translational motion, because there's no way that an internal rearrangement can change the kinetic energy in this way. This is something that comes purely because of the redistribution of mass within a rotating system here. So we can look at another example. We can look at collisions in rotational motion. So again, we talked about collisions in linear motion, where angular momentum is conserved, but kinetic energy is only conserved when it is an elastic collision. So let's look. And what was an example of a non-elastic collision? An inelastic collision was, for example, things sticking together, right? If we have two balls, they hit each other, and they stick together. You know, one is made out of Velcro, or both are made out of Velcro or whatever. If they stick together, that's an inelastic collision. So this example is how we translate that kind of inelastic collision to rotational motion. We have one flywheel with a mass, with a moment of inertia of 3 times I0 that is at rest. And we have one flywheel that is moving, that is rotating with an angular velocity of, let's say, 600 revolutions per minute. And that rotating flywheel gets stuck to the flywheel at rest, or the flywheel at rest is brought in touch with the flywheel that is rotating, so that from that point on, they're rotating together. They're stuck to each other. You know, consider this as the two objects that interact, that collide with each other, and they're covered with Velcro. So they're, from that moment on, as soon as they're stuck together, they're rotating together. So how will this change the angular velocity of this of these two flywheels? This is similar to the situation of having two balls collide, where one is at rest, one is moving with a certain velocity, and we're asking what is the final velocity of the balls as they are stuck together when they're moving away. So let's see if we can solve this. The thing that has to be satisfied always is angular momentum before has to be equal to angular momentum after. There's no net external torque that is applied here. So if angular momentum is the same before and after, so let's call this coupled flywheels. So the angular momentum before is, well, the only one that's rotating, and the only one that will have an angular momentum is the smaller of the two flywheels, the one with the moment of inertia I0. So the angular momentum before is I0 times omega 0. The angular momentum after will be the new rotational, the angular velocity, which we'll call omega, times the new moment of inertia. And the new moment of inertia is just the sum of the original moments of inertia, I0 plus 3I0. 3I0 is the moment of inertia of the big flywheel. I0 is the moment of inertia of the small flywheel. And this multiplied by the new angular velocity omega. So this has to be the same. L before is equal to L after. So that means that I0 omega 0 will have to be equal to 4 I0 times omega. So omega will have to be omega 0 over 4. Or 150 revolutions per minute. If we started off at 600. So that's how we calculate the new angular velocity. Was this an inelastic collision? We already know it's an inelastic collision. It's a perfectly inelastic collision because the things stick together. But we can calculate what the kinetic energy before is and what the kinetic energy after is. The kinetic energy before is 1/2 I0 omega 0 squared. There's no kinetic energy in the one that's at rest, the flywheel at rest. The kinetic energy after is 1/2, and now we have 4 I0 and times omega squared, or that is equal to 1/2 of I0 over 4 omega 0 squared. I'm just replacing my omega with omega 0 over 4, and that gets me 1 extra 4, so it goes into the into the denominator, and that is 1/4 of the kinetic energy before. So there must have been some energy lost to go from this higher kinetic energy before to the lower kinetic energy after, and that is work done by the force of friction or whatever forces there are between those two flywheels. So that will be 3/4 of the total energy before, total kinetic energy before, that is going towards the inelasticness of that collision. So this is an inelastic collision, if you want to call it a collision. We wouldn't normally call this a collision. That's why I put this in quotes. So we can do other kinds of problems connecting linear and angular motion. This is a common problem, and I'll tell you in what format this will also come back. But this is a bullet that is fired and that gets attached to the side of this disc. It's embedded in this disc, and the disc starts at rest but starts rotating. So what's the angular velocity with which the disc starts rotating, and can I use, for example, in this case, can I use this to for example, measure the angular velocity and then determine the velocity that the bullet came in with originally. So one question in the chat about the previous one here. So where is this energy lost due to friction? So what will happen, of course, when we bring these two plates together is that for a brief moment they will actually be sliding over each other. There will be friction, and that will speed up this heavier flywheel until that flywheel is moving at the same angular velocity as the lower flywheel, which of course will also be caused by the fact that the lower flywheel will slow down, and at that point the kinetic friction that was causing them to, or was describing the sliding motion, will turn into static friction, and from that point on they'll just be moving together. Now, as long as there's kinetic friction between the two flywheels, there's energy that is being lost, that is dissipated. As soon as there's static friction that just binds them together entirely, it will just there won't be any work done by the static friction, because there's no displacement in static friction, right? I hope that explains where that energy is actually going to. It is going to friction indeed. So in this example, back to the collision of a linear and an angular system together. So we will describe our angular momentum, of course, still. But now in this case, in the original situation, in the before situation, the angular momentum will consist of the angular momentum of the disk and the angular momentum of this bullet as it embeds itself in the disk. So that will be an angular momentum that is the distance r times the momentum m times v. And of course there's an angular momentum due to the disk, which is I times omega, but because the disk is at rest, there's actually no component from that angular momentum. So if we have the bullet embedded in a disk, the initial or the angular momentum before will just be r cross p for the bullet, and so that's going to be r times m times v, and there won't be any component from the angular momentum of the disk itself because the disk is still at rest. Afterwards, we will have I times omega, which now consists of the initial moment of inertia of just the disk plus mr squared, which is the component of the moment of inertia that comes from the bullet, which is now embedded in that disk, and then omega. And now, of course, again, we can take these two angular momenta, we can set them together, we can calculate what omega will have to be if we assume, for example, that for a disk, this is a uniform disk, so it's 1/2 mr squared for the moment of inertia. Then we will find that omega is v over r times 1 over m over 2m plus 1. So I'm not going to do this derivation because it's just algebra at this point. But if you look at this expression, it allows us to do things like look at the limits, right? So we can look at the limit if m is much greater than little m. So if m is much greater than little m, then we have a very heavy disk and a very light bullet. So what will happen is omega will be, well, if this is much greater than that, then omega will be about 0. So kind of something that makes sense as well. If there's a heavy disk, we won't be able to make it spin with a very light bullet. If m is much less than the mass of the bullet itself, then you'll see that this turns into v over. So what happens then is this term disappears. So we just end up with omega. This is about v over r. And so that just indicates that all of the angular momentum in the final state is equal to mr squared times v over r. So that's just mvr. That's our initial angular momentum. And so we essentially have just a bullet that is only that mass little m that is going around in a circle, and that gives us the angular momentum of just that single mass that is going around. In the case of LB4, because this is an individual particle, an individual mass that is going in a linear motion, we don't have an omega yet at this point, right? So we can't write this term r times m times v. We can't write that in terms of an initial angular velocity, because there is no angular velocity yet. We're still moving linearly. So this is the part where we're connecting linear motion and the angular momentum of an individual particle, of a single particle, with, in this case, the angular momentum of a rigid body. And that's, of course, the part where we're trying to connect here the linear motion with the angular motion part in the before and the after situation. I hope that makes sense. I got a question in the chat about that. Okay. So one final thing for today is gyroscopes. So this is a key example of rotational motion, and in particular of conservation of angular momentum. That comes back in many cases. You might have seen these kind of gyroscopes. If I had an actual lab, then we would bring out a nice large gyroscope, and we have these that we can spin up with a handheld drill to very high velocities, so they can spin easily for 10 minutes or so, which makes it a nice demo piece. But you might be familiar with that. There's an axis of rotation here. Typically, this can stand on some fixed point, but it's rotating freely. This axis can move around however it wants, and there's a heavy disc here that is rotating almost frictionlessly around that axis. And the only reason why the other things are there, they're just guards to keep fingers out. So what this also is, this is essentially a top, right? This is a top with a fixed point where it's standing on the ground, and there's an axis of rotation around which the top is rotating. Now what happens with the top is entirely defined by its rotation. If this top is not rotating, well, you know what happens with a top if it's not rotating and you put it down like this. There's going to be a force of gravity that applies at the center of mass. That force of gravity around this pivot point will, of course, cause a torque. The torque is going to point perpendicular to the vector r and the vector of the force. So that's going to be, in this case, somewhat along the minus x axis there. And that torque in turn will cause the top to fall over. That's a very well-known situation. If you put something that isn't balanced, if you put that on the ground, it will topple over under the influence of gravity, right? That's the torque that takes over, and this torque causes the direction of the axis here to fall over. That's what happens when there's no rotation. When there is rotation, though, there's a conservation of angular momentum law. We need to maintain our angular momentum. So there's going to be an angular momentum that is pointing in the direction of let's think of the angular momentum as instantaneously pointing in the direction of the axis of rotation. So it's going to be I times omega. So if I is the moment of inertia of the top and omega is along the direction of rotation, then I times omega, the angular momentum, will point along the direction of rotation. This torque that is applying here will want to change that angular momentum. But now it's not changing the angular momentum from zero, as in the case when the top is not spinning. It's changing it from a finite value that is along the direction of rotation here. So what's going to happen is this torque will slowly move this direction of the angular momentum vector. It's not going to stop the rotation. It's just going to change the axis of rotation. And what will happen is that the axis of rotation will start to rotate precess around the vertical, around the direction of gravity. And we can actually treat this mathematically without much difficulty. So we can calculate that torque. It's going to be, even in the case of a rotating top, the torque doesn't change, right? The top is the torque is R cross the force, so that's going to be R cross M times G. So really, what this is going to be for a top that is at an angle theta. Here, there's some more quantities shown. for a top that is at an angle theta, that means that this is going to be r times m times g times sine theta. That's going to be the magnitude of the torque. Now that torque is going to be dl dt, right? So if I write this down, so for this precession of a top, the torque is rmg times sine theta, right? So that's r cross the force. That's the magnitude of r cross the force. So that torque will have to be equal to dl dt. So that means that the little change in angular momentum will be tau times dt, will be the torque times dt. So if there's a torque in this direction, that means that the angular momentum vector L will change a little bit in that same direction, in the direction of the torque, but multiplied by dt. So over a time interval dt, the angular momentum will shift to there. So that means that dl will be m times g times r, this expression here, times sine theta dt. And if we now want to calculate what that dl, what that little shift in the angular momentum direction corresponds to in terms of an angle, let's go back to this picture here. So what is the angle phi, or d phi in some sense here, that is described by dl, which is caused by our torque here. So we can calculate that. So we can calculate d phi, which is going to be this little dl over L times sine theta, where L is the magnitude of L and sine theta is this angle here. So this is L times sine theta. This is our dl that we just calculated. So d phi is going to be dl over L times sine theta. So that's going to be or mgr sine theta dt over L times sine theta. Oh, and that's equal to mgr over L dt. Okay. So now that we have that, we can calculate d phi dt, and we'll call this omega phi, and that is just mgr over L. And if I wanted to express this in terms of what L actually is, so that's mgr over I of the top omega. And so this is going to be our expression for the precession angular velocity. So that's the angular velocity now with which the axis of rotation will rotate around the z-axis. So if we have an axis, if we have a rotation omega around the axis of the top itself, it will rotate with a precession angular velocity omega p here. I probably should have written it as omega p as well. So with a precession angular velocity that is given by this expression. So a larger omega will result in a smaller precession velocity. So there's a couple of different conclusions we might be able to draw from this. But I'm not going to dwell too much on this, other than, you will have noticed this when you're spinning a top, is that it actually does this kind of precession, right? It sort of dances around its axis of rotation. And you'll also notice this actually happens with the Earth as well. So the Earth has an axis of rotation that's 23 degrees off of the vertical, and so this actually also rotates and precesses around the primary axis. Of course, there's a little bit of a difference here because clearly there's no mg that is applying on the Earth itself. So there's a different force that is kind of the force that the Earth wants to orient itself around, but the same kind of precession is happening, and so the axis of the Earth is also rotating over periods that are of course much longer than that for a small top. Okay, so that pretty much covers what we wanted to see in chapter 11 on angular momentum. So on Wednesday we're probably not quite gonna start on the next chapter. We're probably gonna focus on some problems on the past two chapters on 10 and 11, just to not have a break in the next chapter. So talk to you all on Wednesday.